Hi everyone, my name is Dana Johnson and I'm a master's student studying at the University of Illinois at Urbana-Champaign in the Department of Natural Resources and Environmental Sciences. Today I'm excited to share with you some exciting results from a pilot study we conducted with residents of interior Alaska. My talk today will be focused on a stated choice analysis of preferences for climate change adaptation in Denali, Alaska. Global environmental change is challenging traditional protected area management paradigms that, at least in the case of the U.S., have traditionally followed a top-down framework. Climate change is causing rapid and unprecedented impacts in protected areas and their surrounding communities, leaving land managers with difficult decisions about the futures of these landscapes. In locations at higher latitudes, such as interior Alaska, these changes are magnified and occurring more rapidly, which has created urgency in identifying novel approaches for managing protected areas in a way that adapts to climate change and aligns with community interests. Decisions about the future of these landscapes will involve difficult trade-offs that underscore the significance of including diverse stakeholder perspectives, including local communities. Past research has highlighted the importance of community and stakeholder engagement in protected area decision-making processes, indicating that effective engagement legitimizes decisions and builds public support for protected area management initiatives. Further, identifying distinct visions is integral for overcoming common challenges that protected area management faces globally, such as lacking common visions and support among local, regional, and national governments, and difficulties in balancing conservation goals with economic and social drivers of change. To identify distinct visions for the future and navigate possible solutions, stated choice modeling can be a useful approach for elucidating trade-offs that different groups of people are willing to make to attain their future preferences. The theory underpinning stated choice research is utility maximization theory, which assumes that individuals will make choices that maximize benefits, and as such, express preferences that indicate associated levels of utility. During a choice experiment, respondents are presented with pairs of hypothetical scenarios and asked to choose the most preferable option. These scenarios include lists of attributes held at varying levels identified in an experimental design. In this example to the right, we see that there are a series of system characteristics, such as fish habitat or population survival score, that represent attributes. Over to the right, we see in these columns the paired comparison. We have option A, which is one future alternative, and option B. If a respondent prefers the configuration of levels in option A, they would indicate their preference by selecting option A. If they prefer the configuration of levels in option B, they would indicate so by choosing option B. A respondent can generally also abstain or choose current conditions by choosing an option C or no change option. The statistical technique has been used across a wide gamut of disciplines, including economics, recreation management, and environmental science. While based in econometrics, the application of choice modeling in natural resource and environmental management contexts is only growing. In the context of protected area management, there's a growing need to understand the priorities of distinct stakeholder groups and residents surrounding protected areas in the face of changing conditions. With such rapid and unprecedented change, distinct priorities for the future need to be empirically assessed to understand local community preferences for the future and trade-offs that individuals are willing to make to attain these preferences. While research using choice modeling in environmental management contexts is growing, discrete choice experiments at regional scales are largely unprecedented, yet important for preparing residents for their futures. Further, research applying choice modeling to climate change-related issues is nascent, but can elucidate key visions and be useful for protected area managers weighing difficult decisions for the future of these important landscapes. This research aims to address this need by using a discrete choice experiment to elicit interior Alaskan residents' preferences for future landscape change in the face of regional climate change impacts. The main objective of this study is to assess the effects of key changes likely to occur in the region as a result of climate change on preferences for the future. These attributes include moose population, off-season tourism, acres managed for fire, length of winter, and annual cost. This study takes place in communities surrounding Denali National Park and Preserve, a 6 million acre park located in interior Alaska. Denali is home to the highest peak in North America and has 2 million acres of federally designated wilderness within its boundaries. Beyond the wilderness boundary, there are areas of the park that are considered preserve and accommodate human use. A variety of ecosystems are found in the park, such as deciduous taiga forests at low elevations to tundra, glaciers, and bare rock at the highest elevations. Denali is renowned for its charismatic species and vast undeveloped landscape. Major changes in the landscape due to a changing climate are altered weather patterns, hydrology, and vegetation. These changes are manifesting impacts on fire regimes, growth seasons, wildlife distribution, precipitation patterns, and more in Denali. Denali National Park and Preserve is adjacent to the George Parks Highway, which is the primary road that runs through interior Alaska. This research includes the communities on or near the road system between Talkeetna and Fairbanks. Within this region, a diversity of interests and perspectives exist that hold priorities for the future, including conservation, education, energy, military, local businesses, and industrial tourism. Each of these communities and interest groups are to some extent impacted by protected area decisions made by federal and state agencies who oversee public land, natural resources, or wildlife. These entities are the primary decision-making bodies and have a large influence over the future of the landscape. To design our choice experiment, we relied on scientific reports and 2 years of qualitative data to identify relevant attributes and levels. We selected the most salient anticipated impacts as a result of climate change that were also relevant to local communities in the region. We developed 5 attributes based on our findings that included various levels that may be realistic over the next 30 years. The table to the right includes each of our attributes, a brief description, and their associated levels. Moose population is our first attribute and describes the amount of moose in interior Alaska. Moose populations are expected to increase in the future. Off-season tourism is our second attribute and describes the growth rate of visitation to interior Alaska during the off-season months. Off-season tourism is also expected to increase due to warming year-round temperatures. Acres managed for fire describes the acres of forest in interior Alaska protected by public land management agencies. The number of acres is expected to increase due to warmer and drier conditions, which will create more forest fires in the region. Shorter winters describes the amount of days in the winter season, which are anticipated to decline as warmer weathers persist year-round. Finally, most data choice experiments include a willingness to pay attribute, and in our case, this is a reduction to a dividend that is received each year by residents from the Alaska Permanent Fund. Dividends from this fund are drawn from state revenue generated from the oil industry. In 2019, each resident who was eligible for the dividend received $1,600. So this is our full choice experiment with their attributes and associated levels. After developing our choice experiment, we received feedback from key leaders in the community who represented the main interest groups. This feedback really helped us in finalizing our attributes and making sure that our choice experiment was relevant to the local community. To determine how to best allocate the attribute levels to the design matrix, we generated an experimental design. Using the software Engine, our final scenarios were calculated from a factorial orthogonal design to identify configurations of attribute levels and paired comparisons. Our resulting design included a list of 18 scenarios that included 2 choice situations, option A and option B, and then of course a no change option. And these paired comparisons were held at varying levels. To reduce the burden on each respondent, we divided these 18 choice scenarios into 2 blocks, so that any given respondent would only respond to 9 choice questions. And of course, here's an example of what a paired comparison looks like in our questionnaire. The resulting 18 paired comparisons constitute our original factorial design. These designs are really useful for populating the hypothetical choice situations shown to respondents. However, these factorial designs are not as efficient as other designs, which are called efficient designs. There are a number of different designs, such as the D-efficiency design, which responds to prior estimates generated through pilot testing to generate a more efficient design. To collect prior estimates to calculate a final efficient design, we conducted a pilot test using a Qualtrics panel of residents living in 10 Fairbanks zip codes considered part of interior Alaska. This pilot test was administered during the last 2 weeks of April of this year and included our stated choice model, sociodemographics, pro-environmental behavior, experience use history, and an environmental attitude scale that was developed to measure specific attitudes towards each of these attributes. To analyze the choice model data, we used a multinomial logit model, which is the most basic logit model with fixed parameters. This model is known as the workhorse of choice models and shows the relationship among the observed attributes unobserved variables, and observed choice outcomes. This type of model is widely implemented but has been heavily critiqued due to its restrictive assumptions. Specifically, this model assumes that the attribute's effects are consistent across a sample population and uncertainty is identically and independently distributed. Additional mixed multinomial logit models have been created that relax these assumptions, and one of these models is a random parameters logit model. With these relaxed assumptions, the error component of a random parameter logit model can be correlated with alternatives in multiple iterations. Second, the random parameter logit model accounts for heterogeneity in preferences, contrasting previous models that assumed fixed utility of coefficients across a sample. We did estimate this type of model, but did not include the output in our final results due to sample size restrictions with this model. However, we do plan to use a random parameters logit model to analyze the full dataset. All of our analyses were conducted in NLogit version 6. To give you a sense of our sample, it included 28 respondents living in Fairbanks, Alaska. The average age of respondents was 34, and our sample included slightly more females than males. 50% of our respondents were white, and 33% held at least a college degree with an average household income between $25,000 and $49,000 before taxes. Respondents had lived in Alaska for an average of 16.42 years, and most had visited public lands, including Denali National Park and Preserve, at least once, and several had visited in the last year. The results from the choice model analysis are included in this table. The impact of the attributes on respondents' choices is reflected in the coefficients, which is right here, which showed the mean marginal utility estimate across the sample. Acres managed by fire and willingness to pay were significant predictors of choice at the 95% confidence level as qualified by these asterisks. The odds of choosing an alternative significantly increased with warm acres managed by fire. The odds of choosing an alternative significantly decreased with higher monetary costs associated with that alternative. That is, choices were most influenced by acres managed for fire and by the annual cost. These were the strongest drivers of change, and respondents preferred more acres managed by fire and smaller costs for these changes. Though non-significant, the probability of choosing an alternative increased with larger moose populations and decreased with more off-season tourism and shorter winters. That is, respondents preferred less off-season tourism, longer winters, and more moose. Our results indicated that residents in interior Alaska respond favorably to future scenarios that included more acres managed for increasing fires, and those that required less money spent from their annual dividend. One reason for this could be that respondents may be most concerned with prominent impacts currently existing in the region. That is, in 2019, Alaska experienced an extreme fire season due to incredibly warm temperatures and less frequent precipitation. According to the Alaska Department of Natural Resources, there were 719 fires in 2019 that resulted in over 2 million acres burnt. The other significant attribute was willingness to pay. Respondents preferred future scenarios that required them to give up the least amount possible from their annual dividend. Residents in Alaska have a strong affinity toward this dividend, and it could be that the significance of reducing this dividend meant something different than a generic cost. Though non-significant, the additional results are useful to interpret. These results indicated that residents do respond favorably to future scenarios that include larger populations of moose, less off-season tourism, and longer winters. Further research needs to be conducted before drawing conclusions about these findings, especially because they were non-significant, but these do highlight respondent preferences and trade-offs they are willing to make to attain their preferences in the future. For example, increasing moose populations is a probable impact of climate change in the region, and respondents preferred favorably to this. Because of this, decision makers do not necessarily need to focus their efforts on habitat alterations that impact moose populations, but rather should give more attention to managing increasing fires. Overall, these attributes were less influential in respondents' choices, and it could be that while these impacts are apparent in scientific reports and projects, the implications of these changes may not be recognized or prioritized by residents. While this was a pilot study with a small sample, it could be that these attributes were not as important because impacts are uncertain, often indirect, and may have delayed effects that are not currently experienced or observed by respondents. It was clear that increasing fires resonated with residents, and to respond to residents' preferences, decision makers could focus efforts on increasing the amount of acres protected from wildfires in the future. Data from our pilot study provided insights on how to best revise the survey questionnaire and were used to generate prior estimates necessary for producing an efficient design. Using these prior estimates to build our final design enabled us to create an optimal design that minimized error. Our final survey will be administered to 3,000 residents living on or near the George Parks Highway in interior Alaska. This will occur in late June, which likely has already occurred by the time everyone's seeing this. And with this full data set, we hope to not only explore residents' preferences for the future with the choice model data, but also explore variation in preferences by segmenting the population by environmental attitudes. I would like to acknowledge those who made this research possible. First, I'd like to thank my lab group and key project collaborators for assisting in shaping ideas, providing feedback, and statistical expertise. I'd also like to thank the key funding sources for this research, including the Belmont Forum, Biodiversa, NSF, the National Park Service, and the University of Illinois. And with that, I'd like to thank everyone for your attention.